Second part of your lecture of the shortest path algorithm, Dijkstra's algorithm, we are studying. Where we can find a path that is shortest in length or in delay or any other metric. So we can choose different metrics to determine the shortest path. That could be delay, that could be number of hops or number of routers or number of nodes or vertices that you have to cross to reach the destination from the source. It is single source. It could be distance. So there are different metrics to determine the weight on the graph. So if you have a graph and your graph could have a weight, so this weight can be any metric. It could be number of hops, vertices, distance from node vertex 1 to vertex 2, for example. And it is a single source algorithm, shortest path algorithm, where your origination is a single source. Shortest path algorithm, single source shortest path algorithm. And as we have seen here, this was our graph, and the maximum number of nodes that we could have to traverse for reaching the destination could be vertex V. So the complexity, time complexity for this algorithm comes out to be V square, or you could say n squared, where n is the number of vertices. So if you are at one node and you have to find the shortest path, the maximum number of nodes that you could in the worst case would have to traverse is n. So starting at n, and you may need to visit vertices, n vertices, to reach the shortest path. So in the worst case, you would have to traverse through all the nodes to reach the destination. So in this case, your algorithm takes n squared time complexity, where n is the number of vertices. Here we have an example of directed graph. As I told you, we can work for directed or undirected graph to find the shortest distance. And one more point I like to mention here, one disadvantage of this algorithm is that the weights that we have on these edges, where these are the vertices and this is your edge, they cannot be a negative value. So this algorithm works on non-negative values for the weight metric. Why? Because as I explained the relaxation condition, we are adding the distance from the node that is visible, plus if we reach to that node from T to U, if you reach U, and then you will have a cost from U to V. So we are adding these two values to estimate the updated cost or distance from source node to your vertex to your destination vertex. So since we are adding them up, giving a negative value would disrupt the estimation of the distances, and therefore we cannot implement this algorithm where the weights are in negative values. So if we have the source vertex 1 and we have to estimate the shortest path algorithm. So for the starting vertex, we will have to determine how many. We have a total of 6. For reaching 2, from 1 to 2, we have a directed path of 50 here, and then reaching from 1 to 3, we have value 45. To reach 4, it is 10, and then to reach 5, initially we have infinity. Since it is not directly connected to your node 1, 5 is not directly connected, we will assign an infinite value to the distance. So in the shortest path, we estimate the shortest distance, cumulative distance, that is given by 4. So 4 is selected as your next vertex for the shortest path. And once we reach 4, we will have more paths to connect to other vertices. So from 4 we can go to only one vertex, that is 5, and one vertex that is already visited, and the distance is 10, which is the same as before. And then at reaching 5, you will have an additional cost of 15. So the total cost would now be, to reach node 5, it is updated to 25. So now we have already selected 10. Among these, which is the shortest distance, cumulative distance? So node 5. So your node 5 is selected as the next node. Now 5 is selected, and you can see we have path towards 2, no, vertex 2, and path towards vertex 3, outgoing. So you can see we could reach from 1 to 2 directly with a cost of 50, but if we reach from 1 to 4 and then to 5 and then to 2, so 10 plus 15 plus 20, it becomes 45. So this path can now be updated because we have a new path which is shorter. And then we can reach 3. So if we add 10 plus 15, 25 plus 35, 25 and 35, 60, which is greater. So this path is not updated. Then we have 10 and 25, which are the shorter path. And now we can we reach 6? Is it connected? Yes, it is connected, but it is unidirectional. Only data is coming in one direction, from node 6 to node 5. So we cannot go from 5 to 6. So this value remains the same. Now among these, which node is selected? For example, second, or node 2 is selected as the next one. So our path is going from here to here to here, shortest path. And then when we are at 2, we can reach in 2 directions, either 4 or either 10. So up till now, it is to reach here we have 45, and to reach 3, 45 plus 5 is 55, which is greater than the already existing cost. Or reaching 4, 45 plus 15 is 60, which is greater than existing path. So in this case, we will select the next one, which is node 3, which is 45, and our costs will remain as such. However, we cannot reach by any way, we cannot reach our node 6 because there is no incoming path towards node 6. So this will remain disconnected, and our path, shortest path, will be from 1 to 4, then you move towards 5, and then moves towards 2, and then 3. So our shortest path using the Dijkstra's algorithm is one, 4, then 5, 2, and 3. So all nodes have been covered which are connected and have a directed path. So in a directed path, we may come across a situation where we cannot reach a node because there is no path that is connecting the node to this node. This is the solution for this graph that is represented here, the directed graph. And here is a sample implementation of your Dijkstra's algorithm. So we will initially be given a graph where in the form of an adjacency matrix. One way of implementing it is like this. You have an adjacency matrix and then you're going to call your algorithm, Dijkstra's algorithm, where you determine the output array, which is final array that I mentioned here, like this array will be your output array. And then we have information about those visited vertices, if it is included in the shortest path. Initially it is initialized as infinity because we don't have path, and we set the first vertex, that is a source vertex, as 0. Always path from source vertex. For example, in this case, this is your source vertex, so initially the path from 1 to 1 will always be 0. So there is no cost in moving to the same vertex. And then we use the minimum distance to find the vertex of the node that is in the shortest path, and whichever node is vertex is selected, it is marked and into the marked as true. And then using this adjacency matrix, the distance value that we have calculated, they can be updated if it is smaller. If it is, firstly, it should not be in the existing list, it should not be true, and there is an edge from U to V, of course, and the total weight of the path from source to that particular node through U is smaller than the current path. And only in that case we can update the existing path. If it is not in this list, shortest path, and given a graph, and it is not infinite, it is reachable, then and the distance is smaller than the existing distance, then we can update the distance value of the adjacent vertices, or include it into the distance, into the shortest path. So for the minimum distance, we first initialize the minimum value. We have to find the vertex with the minimum distance using the minimum distance function. If it is not already there, it is false, and if distance is less than the minimum value, it is less than infinity. For example, initially it will be infinity, but in the next iteration it may, for example, it was 50 and then it was updated to 45 in the previous example. So it is less than the minimum value. In that case, we can update the minimum and extract the minimum index and return that in the minimum distance. Also, this is a repetition of this here. And then this simply, we have a print where we visit each vertex in the distance array. It will display the output. So this is a basic algorithm that we have. The code in C++ we are using to estimate find the minimum index position, and then using that we are going to include that into our shortest path. So we come to the conclusion that this is a single source shortest path algorithm. You can start from any node and find the shortest path through the destination node. There will be only one shortest path. That shortest path depends on the weight value on the edges. Those weight values can be different metric. It could be in the form of delay. It could be in the form of distance. It could be in the form of number of hops. So the minimum distance we can calculate in any way using any of these matrices. And then again, the disadvantage is that for the negative weight values on the edges, this algorithm cannot perform.